Hello and welcome to this video on nucleophilic substitution. This video is going to be an introduction. It's going to be very general. I'm not going to dive into SN1 and SN2 mechanisms because it takes more thinking and it's better to have a basic idea before I get into something very difficult. I shouldn't say very difficult because it's honestly really easy once someone explains it to you. But let's just get into this video. So the first thing I want to talk about is the nucleophile. What is a nucleophile? Well, nucleophiles are substances with unpaired electrons, and nucleophiles can be neutral or charged. So what would be an example of a neutral nucleophile? Well, we could have, I don't know why it's not drawing. We can have ammonia. So NH3. Notice it's neutral. It has an unpaired pair of electrons. What would be an example of a charged nucleophile? Well, hydroxide, OH. So this oxygen has a negative charge, and that would be an example of a negatively charged nucleophile. So let's go on to part 2. Nucleophiles attack electrophilic centers. If I didn't mention this before, these videos I'm making are in a playlist. So in the first video, I showed you what an electrophilic center is, and that's that partial positive on that carbon-halogen bond. So I'll just draw it again just to show you. So here's a carbon-halogen bond. Carbon has a delta plus, bromine has a delta minus, because bromine is more electronegative. And the nucleophile will attack the electrophilic center, which is the delta plus on the carbon. But I don't want to get into mechanisms. I just want to let you know that if we have a negative nucleophile, such as hydroxide, we will get a neutral product. And if we have a neutral nucleophile, such as ammonia, we will end up with a positive product. So if I just draw it really basic and just say, I don't know, let's see here, NU, here's our unpaired pair of electrons, and let's say it's negatively charged. We'll react it with the electrophilic center, and that will be our delta plus, and X is just our halogen, so it's our delta minus. And I should be color coding these so it makes it easier for you to understand. Let me use green. So our electrophile, these lone pairs aren't really necessary, but our R is our delta plus, which is our electrophile. So I'll just say electrophile. And this X is our leaving group. So so much for color coding. Leaving group. And like I said, this nucleophile will attack that electrophile. So show this arrow attacking it. And this RX bond will break off. And what we'll end up with is NU being attached to the R, because that lone pair, and that X being broken off, resulting in X minus, because it gained both of those electrons in that pair, in that bond. So look, we started with a negatively charged nucleophile, and we ended up with a neutral product. Let's use a neutral nucleophile and see what happens. Okay, so let me take this eraser, and let's just erase this. And this is the same thing. We're just using this lone pair. We are attacking the electrophilic center, and this carbon halogen bond. That's what I first used, was that carbon bromine. So this carbon halogen bond will break off, and that nucleophile once again attaches, and we'll end up with a positive product. So let me just put this in brackets, and positive. So main thing to notice is that if we have a negative nucleophile, we'll get a neutral product, And if we start with a neutral nucleophile, we'll get a positive product. So what else? So let's talk about the displaced group, the leaving group. So what makes a good leaving group? Now, this is why I said this is an introduction video. I'm going to make a video on what makes a good leaving group, because there are several factors that determine if it's a good leaving group, such as if it's a weak base. That's a good leaving group. But there's other things I want to talk about, so I'm going to save that for another video. But the displaced group, which is sometimes they'll call it in your class, just know that it is your leaving group. So our leaving group is our displaced group, which is right here, this halogen. So I'm going to work through an example. So yeah. Okay, let's get into these examples. We have our nucleophiles, A, B, C, D, and E, each reacting with 1-bromobutane. Now, where at in 1-bromobutane is our electrophile? Well, let's draw that out first. So, let me get a pen. There we go. So, 1-bromobutane, we have 4 carbons, and then we have a bromine. So, that's what 1-bromobutane looks like. So, this carbon has a delta plus, and this bromine has a delta minus because it's more electronegative. The electrons in that bond will be closer. I don't know how to word things. Will be closer to that bromine. So let's react our electrophile with our nucleophile. And delta plus, delta minus, just a good habit to do that. Our nucleophile attacks our electrophile, and this bond breaks off. Now, why is that? Well, if we didn't do that, we would be breaking the octet rule. On this carbon right here, we have 2 hydrogens branching off of it. And if we just made a bond here and did not break that bromine group off, we would have 5 bonds on carbon, and we should know we can't do that. That's 10 electrons. So we have to show that bromine being broken off. So let's do that. We have our bromine broke off, and we have 1, 2, 3, 4, and our iodine has attached to that electrophile, our carbon. So this is what our new molecule looks like. And remember what I said earlier, a negatively charged nucleophile results in a neutral product. Well, we have a neutral product, so that's good. Let's react this nucleophile with our, that looks bad. I thought my first one was bad, but I guess I can do worse. So here we go again. We have our delta plus, delta minus. Our oxygen has that extra lone pair, so we'll be using that to make the bond. This bond will break off, and we will get our product, which is bound to the oxygen because we use that lone pair to create a new bond. And we also have a CH2, CH3 we can't forget about, and our Br minus. Look here, negatively charged nucleophile, neutral product. All right, now let's do N3. What in the world does N3 minus look like? Well, 5 times 3 is 15. The reason why I said 5, we had 5 valence electrons in nitrogen, 15 total, and plus 1 because that negative charged, so it's 16, and I just know it looks something like this, where this middle nitrogen has a, let's see, I'm forgetting some electrons. Hold on a second. There we go. So our middle nitrogen has a positive charge, and our nitrogens on the side, 1, 2, 3, 4, 5, 6. 5 minus 6 is negative, so we have these negative charges here. So this is what our nucleophile actually looks like. So let me just scratch that off. So we'll be reacting it with 1-bromobutane. Here's our delta plus, our delta minus. Our lone pair, which is on this nitrogen or this nitrogen, obviously not the middle nitrogen because it has no lone pairs to make a bond with. And nucleophiles have to have an unshared pair of electrons to make a bond. So we'll take this nitrogen, make a bond right here onto our electrophile, and we'll break off our carbon-bromine bond. And we'll get something that looks like this. It's always a good idea to count your carbons so you don't mess up, but I'm getting used to this, so I don't really have to worry about that. Just let me know if you see that I've counted one too many carbons, but I shouldn't do that. Anyways, can't forget our Br minus. Now, you might be saying, hey, dude, we had a negatively charged nucleophile, but our product has charges all over it. Well, if we have a positive and a negative, those cancel out to make a neutral. So this would still be a neutral product as a whole. So this still follows the rule where if we have a negatively charged nucleophile, we'll end up with a neutral product. Let's look at D. D is a neutral nucleophile, and neutral nucleophiles make positive products. So react it with 1-bromobutane, delta plus, delta minus. Our lone pair attacks our electrophile, and our bond breaks off. So it will look something like this. Positively charged because our nucleophile was neutral, and now it will form a positive product. Can't forget our bromine. Our last problem, react it with our 1-bromobutane. We have a neutral nucleophile reacting with a, just a normal, I don't know why I'm going on with that. We have a neutral nucleophile reacting with 1-bromobutane. It will attack that carbon, and our bromine will be ejected, and we'll get something that looks like this. Can't forget the positive. We have a neutral nucleophile. We'll make a positive product. And that will be your answer for this problem. Now, I'm going to go into a harder or challenging example dealing with retrosynthetic analysis. And that will be it for this video. So, yep.